Okay, so we claimed, based on some data and some conclusions of how brain responds to use it or lose it kind of idea, we said not only now with digital amnesia or Google effect, the brain is getting rewired and so on. These are kind of considered microevolutionary limits of how things respond over time. And there is a paper now that looks at the idea that around 3,000 years ago, human brain began to shrink because of this social living, shared memories, shared brain, and so on and so forth. And this paper argues that that idea may be a little bit of a misinterpretation of the data. What does it mean? So let's look at the introduction of this paper. Encephalization, growing of the brain size, has long been understood to be a key adaptation in the human lineage, and over the last 4 million years, species attributed to Australopithecus and Homo have shown demonstrable trends toward increased brain size. So crania have been found, and assuming that the brain fills the cranium, it's hard to keep empty space between the brain and the cranium, that brain size also had grown. However, our understanding of past populations is limited by our reliance on the fossil record. For some poorly preserved species, we are currently dependent on a few or even a single cranium sometimes. This places limits on our ability to infer subtle changes in brain size, even as the broader trend of encephalization is clear. So the paper being discussed here is by De Silva et al. From 2021 that hypothesized that modern human brain size has decreased starting at roughly 3,000 years ago. They offer a model in which directional selection for decreased brain size and or stabilizing selection for maintaining large brains was relaxed due to the ability to store information externally in social groups. So you didn't have to remember everything. You had shared cloud represented by the members of a community that were cohabiting, hunting, gathering together, doing agriculture together, foraging together, pasture, grazing together, and so on and so forth. Under this model, which they analogize from ants following the development of complex societies, the cumulative intelligence and knowledge of the social group acted to relax the strong forces of selection that had been present in earlier human populations. So ants and other eusocial insects offer a unique window into how shared labor works, where there are the queen ant, worker bees, and soldier bees, ants, same for bees. They share the workload in such a way that everybody is assigned a particular task. They don't have to worry about anything else. Does this drive some selection or relaxation of a selection criteria in terms of how much of the brain is used and how much is lost because it doesn't have to be used anymore, right? They propose that group level cognition may select for reduced brain size and or adaptive brain size variation. That's a nice idea and makes sense. But now looking at the data again in several steps, this paper shows that a statistically significant change point in the size cannot be found in the same data that was used by De Silva et al. 2021. So looking at the log of the endocranial volume in cubic centimeters going back to 10 million years and looking at the various relatives, hominins, Ardipithecus, Australopithecus, early Homo, early modern humans, later Homo, modern humans, early modern humans and modern humans, Paranthropus, Rudopithecus, and Sahelanthropus. this is not debated at all, that the brain size has grown based on fossil evidence, and also there is evidence that there were revolutions in the brain size where some change points can be identified, one here and one there, and then you see the clustering of data here for modern humans, right? So early modern humans are somewhere here. Original data set from the Silva et al. Residuals from the regression are heavily skewed and heteroscedastic, and temporal intervals between samples ranges from 2.85 million years to 100 years. So that's a massive change in the sampling rate. Heteroscedasticity is basically the change in the standard deviation over the time period of a time series that you are looking at. So that has to be kept in mind. Okay, 578 are in the final 100 intervals out of the 987 total specimens in this 9.85 million year analysis. Also shown is the fitted regression lines from a linear model with 95% significance interval around the slope. If you don't understand the statistical part of it, don't worry. Just the idea that when you look at the data more carefully in homogeneous periods where data are fairly comparable and not apples to orange comparisons, then the conclusion on the brain size change doesn't seem so robust. That's the main point. So change points were found using segmented R package, which is a way to do things. Slope is mentioned, and the change points are located at around 3 kilo years. So here, first one is around 2.1 plus minus 0.1 million years. Second one is around 1.3 plus minus 0.1 million years, and there are respective slopes around associated with them. When you look at this whole period, statistically no change point can be found around 3 kilo years, which is the argument made in De Silva et al. About a social brain and brain size change. Okay, so then what they do is take the data for a shorter period. So now consolidated modern human data for 300,000 years. Modern human cranial size over the last 300 kiloannum using data consolidated into 100-year means. Okay, 100-year bins. This data set allows standard practice in time series analysis by having single values at each time slice. Further, the heteroscedasticity is strongly reduced, so the change in standard deviation over time is greatly reduced, which makes the comparisons more fair, although it is still heavily skewed, as you can see. Also shown is fitted regression line with 95% confidence interval around the slope, and the slopes are given, which is not significantly different from 0. So the slope change is not there, and you can see the scatter here with all the data clustered here, which means you can further go down to 30 kilo year time scale. For the last 30 kilo years, you do the same data again. Modern human cranial size over the last 30 kilo years using data consolidated into 100-year means again. This data set is neither heteroscedastic nor skewed. Further, we argue that this is the appropriate scale at which to examine the microevolutionary hypothesis of change due to selection changes in the Holocene. Also shown is the fitted regression curve line with 95% confidence interval around the slope. The slope is given, and it is not significantly different from 0, so there is no trend. No change point was found for this consolidated and reduced data set. So essentially, the point is that the data is not sufficient in time and space, and considering that agriculture evolved in different places independently as far as we know, and we already talked about civilizations, differences in their cultures, trading versus more agricultural ones depending on what is lacking, whether you have a coastline or not. Various other factors play into these, but the fact is independent civilizations evolved, and it's unlikely that they all had similar social brain and similar social brain relaxation of the brain size, cranial size volume happened across the planet. So overall, the argument is that maybe there is no statistically significant change in the brain size starting 3,000 years ago. I just wanted to include it here because there is convincing case now, there is more data again that people are beginning to remember that they can find anything they want on Google, so they are retaining less of the details. So they use Wikipedia, Google search, and YouTube and whatever else to gather information when they need it, so they don't necessarily have to retain it. So now Google effect and digital amnesia are tested, and neuronal connections apparently do change at these fast time scales, because brain is very plastic and it wants to use the multiple connections, etc., that are available. And there is also debate about whether new neuronal connections happen at a later age, and it is found that depending on the activity you're involved in, like learning a new language, learning a new skill, group activities, whatever, reading, etc., you can still form new neuronal connections in the brain. So brain is a very complicated thing, and it's maybe good news that actually brain size is not may not have shrunk starting at 3,000 years ago. So this obviously affects our behavior and various other things as well, in terms of cultural memes, information age, conspiracy theories, social media influences, etc. So in the last chapter of this book, we will look at what modern human is doing in terms of awareness of its own impact on the environment, and how the modern human is dealing with the impact, and attempts to mitigate the impact and adapt to the changes already induced and have become inevitable, and so on. Okay, so let's leave this here for now.